the Netherlands, a flat country. Situated in the river delta of the rivers Rhine, Maas and IJssel. The water table is just below the surface. Over 15 million people live in this country. More than 350 persons per square kilometer. Over 6 million motor cars. Over 1 million lorries. 2,000 kilometers of motor roads. 3,000 kilometers of railways. And yet, more roads and railways need to be put in. Because the people of Holland travel. They travel to their jobs. They travel to the beaches. They travel to meet their friends and relatives. And roads are getting more congested. And railways have insufficient capacity. Plans for new infrastructure are hard to realize. Every plan, however, for new roads or railways finds greater opposition. The people of Holland do not mind new infrastructure as long as they don't hear or see it. Going underground would be the answer. Building infrastructure tunnels is not cheap, especially if the land has a high water table. The Dutch have mastered building tunnels under their rivers and in wet country of the sunken type. But now the Dutch need a new type of tunnel, the surface tunnel over longer lengths. It is time to introduce a new technology. Now, it is time for TOMAS. TOMAS, the technology for making trenched infrastructure in wet country over greater lengths. TOMAS, a new shape comes into being. TOMAS, the shape made by an automatic construction method. TOMAS, a construction method based on simple prerequisites. To construct the trench within the smallest space, thus avoiding high land cost and nuisance to the adjacent landowners. To construct the trench without draining the water, thus avoiding problems with adjacent buildings and high cost. To construct the trench with well-known building technology, thus avoiding the development of risky new techniques. And above all, to construct the trench for a lower cost than so far customary, and within a shorter period, making it possible to apply trenched infrastructure more often. To make all this possible, the inventors of TOMAS developed a unique purpose-designed and patented digging machine, which they have named in Dutch the Uitslover, or in English the druncher. Let's have a close look at how the druncher makes its way through the land. After evacuation of a layer of topsoil, reinforced concrete piles are driven into a load-bearing stratum. These piles are driven into deep-laying solid sand layers, centered approximately every 3 meters apart, at alternate rakes, to form a stiff triangular-shaped structure on both sides of the trench. Along these piles, on either side of the cutting, precast concrete beams form a guide system for the next phase. Then the druncher is put together in a starting pit. This machine follows the precast concrete beams as a guide rail to absorb the reaction forces during the operations and will follow any required curves. On the front end of the druncher, a traditional rotating cutter-dredger head digs its way through the landscape. The soil is removed by the cutter and pumped away by a regular dredging pump. The rear end of the druncher has a special designed large wheel on which the precast concrete semicircular segments are placed. These segments are called tubings. Tubings, weighing about 2.5 tons each, are delivered to the site by truck. Each tubing is carefully placed on the large special design mounting wheel with a diameter of about 12 meters. The tubings are placed upside down on the wheel by a computer-controlled automatic pick and lay down system built into the overhead gantry crane. After all the sections are placed on the wheel and held in place by vacuum, a 180-degree rotation places the elements now right side up and next to the previously placed elements. Elements are placed next to each other and are sealed against each other with rubber ring seals, well known in underground tunneling. The segmented sections are connected lengthwise by means of permanent tension bolts to keep a tight fitting in the longitudinal direction. The two straight elements are placed on top of the half circle to complete the circular shape of the concrete segments. As soon as the segmented sections are in place, 8 hydraulic cylinders mounted on a horseshoe-shaped pushing ring move against the sections to secure their position. Immediately after that, steel pre-stressing cables are fed from one side in through holes in the beams to the opposing side of the construction, where they are fixed. Then, these cables are hydraulically tensioned on the prescribed tension force. Now, the drencher is ready to move one station forward. Clamps holding the drencher in position on the precast concrete beams are released. By increasing the hydraulic pressure on 8 hydraulic jacks, the drencher is moving slowly, one length of a segmented section forward. At the end of the move, the clamps are fixed on the concrete beams again. Meanwhile, the laying of the next row of segmented sections on the big mounting wheel has continued because the big wheel had rotated back to its original position. The drencher is now ready for the next cycle, and another 1.6 meters is added to the construction. We will now demonstrate the procedure in slow motion again. The placing of the segmented sections on the big wheel. The rotation of the big wheel. The placing of the straight elements. Pushing the sections up against the precast concrete beams. The hydraulic pushing forward system moves in. The release of the clamps. The reinforcement cables are fed into the sections. The tightening of the cables. The moving forward of the drencher. The fixture of the clamps. And meanwhile, the placing of the segmented sections continues on the big wheel. We will now once more look at the whole sequence again, but now in a faster mode. You will notice that all construction activities are taking place in a completely dry and open area. One person can control the automatic placing procedure from the wheelhouse. Meanwhile, another person down below can control the placing of the units and make sure that no dirt comes in between the rubber seals. The whole process is fully automated and is pre-programmed by computer for various site conditions. The cutter dredge on the front side of the drencher continues to work while the mounting of the segmented sections is taking place. In this way, approximately 50 to 60 meters of trenched infrastructure can be realized each full working day. After the drencher has passed, the construction is filled with sand, including a drainage system. For railway infrastructure, a rail bed, sleepers, and rails are installed. Roads will be completed with surfacing as required. The result of this is a relatively low-cost trenched infrastructure with the following advantages. Fewer noise emissions from the out-of-sight traffic. Excavation and land use are minimal. Level crossings with other infrastructure is simple. Easy covering of the trench is possible with precast concrete elements. Safe in case of derailment because the traffic will be contained within the cutting. If in-ground infrastructure is required over greater lengths, think of TOMAS. If infrastructure in residential areas must be put out of sight, think of TOMAS. If your construction budget is limited to realize all this, think of TOMAS. Now, it is time for TOMAS.